And it's my pleasure. We have today a talk by Professor Victor Kovtunenko at the University of Graz. The title is on the screen. So please, Victor, go
Uh,
ahead.
Thank you very much for your introduction and invitation. Yeah, you see the long title. I will also not try to read this, just explain you what's going on. Yeah. Some structure of the talk, so generally can be kind of split it in three parts. Yeah. Before starting with scholastic theory, first I give you motivation, motivation for modeling, and it is motivated, in fact, implicit constitutive responses from the nonlinear elasticity, nonlinear solid mechanics, which are suitable to describe some new materials like polymers, porous, and um, porous metals, and so on. From this motivation, I will introduce a general implicit theory, then its application to the our model, which is linear in both stress and strain, but still not linear because we have a product between stress and strain. Yeah. And we will see that it needs some regularization to prevent possible blow up and final time. And I give you some examples to illustrate how this model works. And motivated by these models, I will overlay respective viscoelastic theory, which presented by linear time integrals, and yeah, have the special then we have special structure of convolution of this viscoelastic integrals with nonlinear constitutive response, which we will consider for well-posedness in the variational formulation based on the coercive and maximal monotone graph theory. Yeah? And somehow the third part, it gives a bridge between the viscoelastic and elastic theory that allows us, on the basis of the correspondence principle, construct solutions of viscoelastic problem semi-analytically based on solution of elastic problems from the first part of my talk. And then I will give some numerical example to show the behavior of viscoelastic models, nonlinear viscoelastic models. Okay, let me start first with the abstract theory of implicit material response developed in the work of Rajagopal from the Texas A&M University. Generally, it's very abstract law, this calligraphic implicit function f between the Cauchy stress sigma and deformation gradient f, and also depending on the mass density rho. And generally, such models are not assumed to be inverted in terms of stress or in terms of strains. Yeah? Of course, it is too general, so we start simplifications. First, based on the general result of Haley-Hamilton theorem for the tropic F, introducing the left Cauchy green deformation tensor B, this structure can be represented in the following form. Here, this long equation with 8 terms. Yeah, it includes a combination of sigma and B up to the second order, and 8 with 8. No, 9 parameters, lambda 0 from lambda 8, which depends freely on the traces of all these products. Yes, it is very general representation form for such implicit functions, but still too general. So next time, step in simplification, we assume that the deformation gradient are small, and introducing the linearized train, this epsilon, we can express the above formula in this 9 terms. Again, it depends sigma up to squared epsilon with arbitrary coefficients beta I, which now depends only on 3 invariants of stress of sigma. This below 3 invariants, usual one. And we can observe that in fact this equation already is linear strain. So here it can be, in this case, it can be already managed some way. For example, I wrote here some special subclass of models when we assume that coefficients higher than before are 0, and then we have in fact these 3 terms written in the above equation, where I can now invert with and express the strain in the term of stress by this formula, but still this is nonlinear in sigma. And here we also split the tensors, second order tensors, matrices, in the deviatoric part, sigma is equal sigma star is deviatoric part, plus spherical part trace of sigma, 1/3, and identity tensor. So, for example, we can consider such equation, such as nonlinear, where beta is bulk modulus, which depends nonlinear on the mean stress trace sigma. Here there came some usual constant, Lamé constant mu, Young modulus big E, Poisson ratio nu, and constant bulk modulus K when it is constant. For example, from analysis of experimental curves, there is written some heuristical function of beta depending on the trace sigma, and this arctangent form, and illustrated below. And this is bounded and also separated from 0, monotone increasing function, and so this mathematically good term, which can be we have investigated. Okay, now the next step in simplification. In fact, we can consider that coefficient depends also on the linear on the sigma. And in this case, it can be was formulated by in the box by Radikapal, this above law, which connects epsilon sigma deviatoric stress and trace of sigma with coefficient which depends on linear on traces of sigma at epsilon. In fact, this is already this expression in linear is both in stress and strain, but it is generally non-linear relation because we have product of epsilon times sigma, and here epsilon by sigma. So it can be some already starting point for our investigation. This equation has 3 arbitrary constant lambda 1, lambda 3, lambda 4, which can be fitted from some result. And to analyze somehow this relation, let us firstly take the trace of this expression. Again, we have such bilinear function, so to say, yeah, between traces. And moreover, we can, for simplicity, avoid, for mathematical reasoning, yeah, avoid these two constant lambda 1, lambda 3. It remains only free constant lambda 4, which express non-linearity. When it is 0, then we have just a linear model. With help of this relation, now we can invert the constitutive law, either in terms of strain or stress. First, when using from the above formula with lambda 1, lambda 3 equal to 0, expression of trace epsilon through trace sigma, we substitute this as above and get the expression epsilon in terms of stress sigma. Such laws are reasonable for polymers, and another way we can linearize the above expression with trace epsilon, because we assume it is small. We have linearized and write the below equation for sigma in terms of epsilon, which is suitable for porous solids, because in fact, by the balance of mass, the linearized after linearization, we have the inverse dependence between the density, which characterizes porous solid, and trace of epsilon. And therefore, so-called dilatation, trace of epsilon can be considered as a density-dependent parameter. Therefore, we have a coefficient which depends on the density, which is suitable for porous solids. And in my presentation, I will fix on the above, on the first case, on the epsilon is written in the terms of T. Okay, let us look for this bilinear equation for traces. Just sketch it on the plane as here. Depending on the sign of lambda phi, we have either this blue two blue curves for positive lambda phi, or for negative, we have these two magenta dashed curves. Yeah? In both cases, it came, of course, through 0. Yeah? And yeah, if the mechanical engineers are happy, they say, okay, we have coefficient that depends linear on the stress strain, so it's very simple. This is a problem, of course, which happens here, because in both cases we have some points when singularity points, of course, singularity for inverse function. We have the vertical asymptote either this one or horizontal one. That means if trace of sigma approaches this critical values, it goes to infinity. As well as the trace of epsilon goes to some critical values, also go to infinity. So we have blow up and unbounded coefficient, which of course generalists cannot manage. And therefore, what we suggest to do, we just apply regularization by thresholding. We use this cutoff function b. It is just what we have seen part of the curve before, and when it's reached the critical values, it is just cut with some constant underline m and overline m, underline and overline m. So I sketch this on the below two figures. First is for a negative lambda phi, second is for positive, but generally behavior is the same. We see here the red line is this nonlinear law without regularization, and when it closes the critical values, then it switch to linear. And can go further, as well as this point again approaching critical trace epsilon. It switched to linear. It can go further. We have this red line on the left curve, on the right curve, using this regularization big P, yeah, this law. Okay, and we can manage such laws and state the problems, and so well-posedness. I will return back later. Now I just make illustration how such law looks. I for the simple example of triaxial uniform loading. This unit cube is minus T pressure prescribed, so sigma x is prescribed by this low T with T, some loading parameter. Then we'll have a look at displacements in the linear form, the first one, and plus some rigid displacement, which is disappears when we apply the symmetric gradient operator. And substituting this in the law before, we can epsilon dependence on linear sigma, we can find just the displacement u as a function of t. In this expression, and by applying thresholding, respectively, the expression below. So again, we have the following solution that with time, with this full picture just for positive or negative values of the parameter. If we do not apply thresholding, we have this blue dashed line which has blown up by certain values of t, yeah, and with the help of thresholding, we just switch to linear branches and can avoid this unbounded phenomenon. Okay, good. It was the first part. Now let us go to the viscoelastic modeling. Somehow motivated from the previous consideration, we can consider the responses. This epsilon independence on sigma. So we have considered before the specific form of coefficient E2 dependence on trace of sigma. And as well, it can be considered the nonlinear coefficient E1 in front of the deviatoric part, sigma star, that it should depend not on trace but on the norm of the deviatoric part. And more generally, we can consider arbitrary suitable response, which we denote by operator calligraphic f. So this is response function. And we consider the viscoelastic equation, which means that strains epsilon now depend on t by applying some operator, this calligraphic e dependent on time to this response function e, which is in fact f of sigma. So here we have we have e of e, and if you substitute here, we have e with f applied to the epsilon. Yeah? Convolution. We have convolution E and F function. So we consider viscoelastic equations of such form given by convolution of the integral operator E depending on time and response function calligraphic F, which integral general abstract form of this integral operator E written in this equation in this gray box is expressed by this general form. The first term and the second integral in time with some kernel, this bold J. In general, this tensorial kernel. So if epsilon is is second order tensor, then bold J may be fourth time tensor, depending on the time. In particular case, if this kernel is isotropic, then we have just scalar G and apply the usual Volterra equation written below, yeah, where G is now not tensor but just a scalar function of time. Still, this equation cannot be inverted to express strain in terms of stress. Yeah, so we have to consider independently strain and stress, and connected by this equation. Which are examples for this heredity integrals? First example, so-called time shift approach, written above as some specific exponential form here and here. Yeah, I will not comment. Mostly used or often used are representation of the kernel by Prony series, written here for n from 1 to the capital N, this with this exponential function for the kernel. That particular we can note if n is equal to 1, the only one in term. After differentiation, this expression is restricted to time, we derive just the Kelvin-Voigt model derivatives. And if we take n equal to, so two terms and twice differentiation, this integral equation, we can arrive to the second order equation describing Burger materials. Yeah? So it is often mostly used expression for the integral. There are also another possibilities. We can associate this integral to fractional derivatives, between 0 and 1 by prescribing this E as Liouville-Weil integral written below with this nu, which corresponds to fractional derivatives. Yeah? So there's examples which are all suitable for our general consideration. Okay, now let us give formulation of the model. More rigorous formulation. So we assume some time-space cylinder. For solid body, we assume that it occupies some bounded domain omega in RD, in d-dimensional space 1, 2, 3. Boundary is d omega, normal, external, outer normal is n vector. We distinguish Neumann in Dirichlet apart, gamma n, gamma d of the external boundary. Time we can see is time interval 0, big T with the final time big T. X is a space coordinate of d components, and so we consider cylinders with the upper subscript capital T. It means that it's changing in time from 0 to T. The cylinder omega T is its side surfaces corresponding to Neumann condition, Dirichlet condition, gamma capital T and gamma TD. So we also prescribe some body forces F as a vector in the cylinder. We give prescribe boundary force G on the side surface gamma n. And also we prescribe some function of response. Generally, it can be multi-valued, calligraphic F, which is mapping between the two-dimensional symmetric tensors, as well as creep function, capital E, which is in continuous, and also maps between d times d symmetric matrices. Okay, this is preliminary. We consider the symmetric stress tensor sigma is dependent on time and x from the space RDD symmetric. Displacement u is a vector of the components which builds a linearized straight again as a symmetric tensor by this formula of symmetric gradient. I consider the equilibrium equation. So it means the divergence of sigma is prescribed f without inertial terms. And viscoelastic constitutive equation, as I told, that the strains are prescribed as convolution of creep function operator E and response function F applied to the sigma, and supported by mixed Dirichlet, homogeneous Dirichlet, and homogeneous Neumann boundary conditions. Okay, so we look for variational solution. As I told you, we have generally the relation cannot be inverted, and therefore we consider two independent variables, U displacement and sigma strain. So this is a mixed variational formulation. In this space where H1 gamma D is just the node zero traces on gamma D Dirichlet boundary conditions, the node just Dirichlet boundary conditions H1, and for sigma we have consider L2, and variational form of the equilibrium equation if given by this variational equation. For sigma times epsilon, and here the right hand side, color product for tensor. And for viscoelastic relation, generally we can generalize to some the selection on the time-dependent graph. Sigma and epsilon of U form some selection on the graph. This Gothic G time, which is formed by always all such relation between epsilon and sigma. Okay. And we can formulate existence result for such variational solution, assuming continuous in time operator. We assume that the graph includes the origin. The graph is coercive with respect to both sigma and epsilon, with this uniform low estimate in the assumption 2. Assumption 3 is that the graph is a monotone for the pairs on the graph, and assumption 4 that the graph is maximal monotone. It means if this monotone inequality holds for all pairs sigma 2 epsilon 2 on the graph, then sigma 1 epsilon 1 belongs also to this graph. And under this assumption, this solution to the problem may be not unique, and we can show it based on Galerkin approximation and Browder-Minty fixed point area. And generally, this is idea follows somehow considerations of the works by Bulicek, Malik, Sully. Refer here. Okay. Now, what is the problem here? Okay, so we have abstract existence, but the difficulty is, of course, when we have integral operator or the operator to check this condition. It's that for some concrete function, it is not trivial task. Yeah. And difficulty here, and in fact, we can consider another approach or another point of view how we can achieve the solution of this viscoelastic problem. It is taken based on the correspondence principle. This means that we consider corresponding elastic problem and just get an analytical formula for the viscoelastic solution. Yeah? So this is the idea what we will now realize here. So now we go a little bit back and consider again non-linear elastic state sigma and U. Now we subscribe E means elastic. Yeah. We assume again the similar condition. We have equilibrium equation for the elastic stress with the same right hand side. We have again mixed Dirichlet Neumann boundary condition the same. In the weak form, using this equation, we can write this variational equation. And again, constitutive equation, now we have only a response between elastic stress and linearized elastic stress and linearized strain given by this response function f, telegraphic f, which again can be consider it as a selection on the graph, this Gothic G, composed by all this power, and will some selection. And again, we can apply formulate the same theorem, assuming continuous operator f. Again, we have assume 4 properties hold that this graph G includes the origin, is coercive, is monotone and maximal. Maximal monotone that guarantees us a rational solution to this nonlinear time-dependent nonlinear elasticity problem. And in this case, now the conditions can be checked for concrete response function f. For example, if we take the response considered in the first part, this nonlinear function written above as f, we can check that 0 belongs to the graph, derive Karapetyants with these constants m1, m2, check the monotony and maximal monotony property. So in fact, it satisfies or guarantees the existence of this nonlinear elastic solution. And now to the correspondence principle. So here I write what we have. The elastic solution with upper indexes E is equilibrium equation in the weak form, and the response equation is written in the strong form. And if the operator calligraphic E commutate with the strain tensor epsilon is written here, then we immediately get the solution of viscoelastic problem with the E convolution F when the sigma stress is coincide with the elastic stress, and displacement U is given just as this creep function E applied to the elastic displacement U with upper superscript E, because when we have this commutative property, of course, we can interchange the operator epsilon and E and get immediately that the corresponding displacement satisfies this convolution equation. And yeah, unfortunately, this property, commutative property C, is satisfied only for scalar operators. Yeah, prescribed by this Volterra equation, but arbitrary Volterra equation, scalar. We can apply this theorem and derive and construct solution of viscoelastic property from the elastic solution. But we cannot apply this trick, of course, if E is not scalar but the tensor operator. This is another story. Yeah, okay, let me show you some illustration of this model, viscoelastic model. Again, we consider isotropic extension or compression. So it means that the sigma is prescribed by a function p depending arbitrary on t. So this mean stress, pressure, if you like. Yeah, pressure. And we'll look this linearized strain in this form with unknown function u, which expresses in fact dilatation u of t. So no dilatoric paths. And let us consider the Volterra convolution in the convolution form, this Prony series with one term, which in fact describe the Kelvin-Voigt viscoelastic material standardly considered in many applications. So now we make time discretization, assume piecewise affine approximation of the unknown function u as written here, and apply numerical quadrature written before for this integral, finding this integral. And yeah, in this basis we calculate the solution U dilatation depends on the applied pressure P. Yeah. So let me show this on the graph. First, these three above graphs, it means that in time, we measure it in hours, t, we have just linear pressure, yeah, linear pressure, written on the shown on the upper left corner. Now, if we calculate the original model reference, you see that somehow we reach critical value here is 1 hour when we have blow up of the solution in finite time. Yeah? And for improvement, if we consider in the upper right corner the thresholding response model, then approaching this critical value, we just somewhere at some point switch to linear model, and so we have some bounded solution in all time interval. Time, it means loading parameter t. And another test, low 3 graphs show us the creep test. Now we apply the following law. First, as before, we have just linear loading up to some value. Here it is close to 1. Then we maintain the load during some time. Here it's about up to 2 somewhere. And then removed loading, yeah, and then unloading. So applied in such pressure P, we first calculate the creep behavior of the reference equation. Here we have typical pictures for creep behavior, as well as in the thresholding response. We have also schematic same creep behavior, but of course with another values, and here we do not reach critical one. Therefore, both model works, and behavioral principle is similar, but with numbers are quite different. Okay, maybe here I will just make a conclusion to my talk, remind you what we have done. First, we consider constitutive relations for implicit material response between the histories of stress and strains to derive the reference model, which is linear in both strain and strain, but still it needs regularization by thresholding to avoid possible blow up at finite time. Then we consider can state existent results based on the properties of coerciveness and maximal monotony on graphs, low and single multi-valued functions. And we consider on this basis we consider quasi-linear viscoelastic models. Quasi-linear means that this operator is linear but depends on time non-linear. Yeah? Described generally by tensorial hereditary integrals of agent or convolution type kernels. And for scalar polytonic equation, we have established correspondence principle, providing some analytic formula for the viscoelastic solution. And we give illustrative numerical examples for test problems by uniform isotropic loading or unloading, and for creep test. And so there is some references, and here I will stop. Thank you for your attention.
Thank you very much for the interesting talk. Now it's time for questions. Probably I would like to start. This Volterra integral equation, what is the right-hand side there? Because as I understood, we saw just the definition of the operator, but what is?
Yes. Yes. So
It's. I think it was on this slide 9.
No, it might be 9. Yes. Yes. Exactly. Somewhere here. Yes. So, you see, we have generally two equations. One equation of equilibrium equation, divergence of sigma is equal to F. Here we have right-hand side F, yes? And sigma and epsilon are two unknowns. And we have a relation between them. Epsilon in the left-hand side is a function of, if you substitute here, sigma. And the operator connected this E convolution with F. It means this is in E written here, we should substitute instead of this epsilon F sigma. We substitute here F sigma and here F sigma. And then we have epsilon is this expression on sigma.
Okay. Thank you. There is a question.
So we cannot substitute it as usually in if we can substitute sigma in terms of epsilon in the equilibrium equation, then we have one equation with the right-hand side F. But here we have mixed formulations that have independent two equations and two variables.
Thank you. And, the question from Sergei Mikhailov, please.
Yeah, I have a couple of questions just for understanding. First of all, on this slide, near the bottom, it is written an operator, and it is written that it cannot be inverted. What does it mean? Cannot be inverted analytically, or the inverse operator doesn't exist? So the inverse operator still could exist, but how to get it analytically?
Yes. Because again, this idea when we can invert and write sigma in terms of epsilon, substitute in the divergence, and we have just one equation for you. Yeah, we cannot do this.
Okay. Another one question. You consider nonlinear problems, and somewhere further on in your slides, you mentioned that you use the correspondence principle. But the correspondence principle is well justified for linear problems.
Sure.
And for also with some limitations, say the boundary between prescribed displacement and tractions should be fixed. Otherwise, it's also hard to justify. The reason for this is that this correspondence principle is justified by applying the Laplace transform in time. But for nonlinear problem, Laplace transform doesn't help much. So my question is, how justified is this principle for nonlinear problem?
So first, thank you for your question. Of course, first we should say, of course, generalized correspondence principle. It is not classical one, because classical one, as you did, we just apply Laplace transform to the linear equation. Here, generalization in the following sense. Let me show you. That we construct the viscoelastic solution from elastic solution, yeah, from the elastic solution for nonlinear problem. And instead of Laplace transform, we apply can generally be used any hereditary integral E, yeah, linear operator E depending on time, any integral, not necessarily produced by Laplace transform. And where it is, yeah, it is maybe, yes. And correspondence principle, that means that we directly construct the solution of viscoelastic problem from the solution of the elastic problem. Yeah, so it is a generalization of the correspondence principle. If you think about correspondence,
still, do you mean linear?
No, not linear. Because this operator E is of course linear operator, but it depends on time in non-linear. Yeah, as we see, the kernel should be rather arbitrary.
So it is a hypothesis and an assumption, or it is proved somehow?
Of course, there's an assumption when we can apply this construction. You see, we assume that is continuous with respect to time, and this is commute with scalar. It is a scalar. Then you use on this commutation property.
Are linear between displacements and strains.
Yes,
of course. But further on, when you consider stresses and strains,
this is non-linear.
Their relations are nonlinear.
Exactly. But E is linear operator, of course.
Okay, thank you.
Thank you. If there are more questions, yeah, please. Alexey.
Yeah, but can I ask also the same question about the operator at the bottom of this page about the invertibility? Understand that it cannot be analytically inverted, but maybe there is a way to construct kind of approximation inverse operators in some sense, in norm of some Banach space.
Yes.
To have a approximate identity.
Yes, sure. It means only analytical inversion,
yeah. Yes, that enclosed form, like.
Yes, exactly.
Exact formula, okay.
Thank you. More questions? If there are no more questions, then let us thank our speaker again. Thank you.
Thank you very much. Yeah.
Thank you very much.
Thank you very much.
Thank you.
Thank you. And see you in 2 weeks.